Thank you for joining my presentation today. My name is Daniel Ode, and I am a computational food scientist. Today, I will guide you through the integration of Cultivate with a life cycle assessment approach. We are going to discuss how Cultivate leverages detailed data collection and analysis to significantly enhance the accuracy and effectiveness of environmental footprint estimations in the cold chain management. But before we delve into the nitty-gritty of this topic or this approach, let's look at the outline for today quickly. I'm going to begin with an introduction where I will frame the central trade-off, which is the energy used for cooling justified by environmental benefits of reducing food loss. And then I'll walk you through how we approach this systematically using life cycle assessment or the LCA approach. And then finally, I will show you how we are implementing the LCA within the Cultivate app. Great. Now let's introduce this very interesting topic. Cooling preserves food, but at what cost? For me, this is a central trade-off that we are going to explore today. Is the energy used for cooling justified by the environmental benefit of reducing food? So first, let's look at two scenarios, right? So farmers without cooling face high post-harvest losses, and then farmers with cooling can extend shelf life and reduce spoilage, but at the cost of using more energy. So the trade-off is clear to me. Fewer emissions from wasted food versus new emissions from powering cold rooms. So cold storage has huge potential, as you probably know. It can reduce losses of perishable produce, which in turn then improves food security and farmer income. But as I said earlier, cooling consumes energy, but at what cost, right? So for me, this is the key question that we must answer. Do the benefit outweigh the environmental cost? So to do this, we need a systematic way to compare the emissions avoided by reducing food loss with the emissions created by running a cold room. And that's why we use the life cycle assessment or the LCA approach. With LCA, we compared two scenarios, one where the produce is cooled using decentralized cold rooms, and one where no cooling is applied and losses are higher. So to make this assessment meaningful or to make it more transparent and realistic, we need a detailed operational data, right? Things like the energy source, the consumption level, the the insulation quality, the storage volume, and even the set temperature. So these are parameters that we need to be accurate. We need to measure these parameters accurately in order to make a very good prediction. So that's why we've expanded the Cultivate setup panel. Now the way it is implemented in the Cultivate app, every code room registered on the platform contributes reliable data, which feeds directly into the real-time environmental impact assessment approach or method that we've integrated. This then ensures that our model reflects actual condition in the field. Great. In the next section, on the next slide, we'll delve deeper into three things. One, the LCA methodology, that we use, then two, the type of data that we collect, and then how we calculated the CO2 equivalent emissions for each room using the Cultivate app. Great. Now, this slide shows you the typically four basic steps of implementing of applying LCA method, right? LCA is already standardized. So to estimate the greenhouse gas impact of each cold room, we use the LCA approach, following the internationally recognized standards, ISO 14040 and ISO 14044, right? And this is often structured in four iterative steps. The first step is to define the goal and scope of the system under study. So in our case, the goal this is the centralized code room, right? And then the second step, we compile the life cycle inventory, or what we call the LCI. This means collecting data on all the inputs, such as energy, material, and also on output, such as the emissions to the atmosphere, water, soil, as the case may be. And then thirdly, we conduct a life cycle impact assessment, so LCIA. Here we translate those input and output into potential environmental impacts using characterization factors, right? And then finally, we move to the interpretation stage where we connect results back to the original goal of the study. So in this case, the goal is to determine whether cooling deliver a net climate benefit, right? As we already explained earlier. Just to note that the key indicator we focus on is global warming potential, or GWP, which basically expresses emissions into kilograms of CO2 equivalent. So this allows us to then directly compare the climate impact of food loss without cooling versus the energy used in running our cold rooms. Now, on the right side, you get to see uh, an example of a typical type of a decentralized solar powered code room, which we model for this solution. Great. Now let's look at the steps that we use for this approach. The first step, as I said, is defining the goal and scope. For our study of our solution, our goal here is very specific, right? So, which is to assess the greenhouse gas emissions from storing fruits and vegetables in solar-powered cold rooms compared to storing without solar power cold room. So in this case, natural shed, right? And the functional unit we use is 1 kilogram of fresh produce stored per day. So basically, this gives us a consistent basis for comparison, right? So this is also very important to be very clear on. So you need to define the functional unit as clear as possible, right? Now, what's our scope? We focused on the storage phase only, right? We know that there are different pre-storage stages before the fruits are being stored. But for this solution, due to the complexity in getting accurate data pre-storage, so this our model focused more on the storage phase. So we excluded cultivation, transport, and even the post-storage, which is consumption. Again, since all these stages remain equal across scenarios, so this gives us a very fair basis of comparison, right? Note that the key drivers we considered are energy use, refrigerant, food loss, and waste, with the system boundary defined around the cold storage unit itself. I also wanted to state that for our solution, we also assess different system configurations, right? So, such as the solar-powered cold rooms, the cold room with battery storage, the cold room with ice storage, thermal storage, and then we have the ice block. Then we have the cold room, the solar cold room with phase change materials such as wax, PCM, and so on and so forth, right? And again, for comparison's sake, the baseline scenario of no cooling were produce kept in natural shed. Okay, great. Now let's look at the second stage, which is the inventory analysis. Now, with this, we have three um, um, basic steps within the step two. So we have the input flow, the output flow, and then of course the data source that is required in this stage. So our input flow include electricity for cooling, maintaining the storage temperature, um, respiration load, um, battery charge, refrigerant leakage, uh, and so on and so forth, right? But for us, these are the basic parameters that we define for this calculation, basically, right? Now, maybe let me delve a little bit into each of them. Uh, Electricity for cooling down the fruit is basically the initial electricity required to cool down the food from the initial temperature to then the room temperature, right? And then we have the electricity required to maintain cooling. Then we have the electricity required to offset respiration due to heat load. And then we have the electricity required for producing thermal storage, and then we have the electricity required to charge the battery, and then finally the refrigerant leakage, which contributes heavily to the emissions, right? Note that in this for our approach, we did not consider the electricity due to infiltration or the transmission load, mainly again due to lack of consistent field data. Great. Now, for our output flow, it includes cooled fruits and vegetables, food loss and waste using the cold room, refrigerant leakage, and emission to air. So I also wanted to emphasize that here we track food loss with cooling, using about 7% on average versus food loss without cooling, which was about 50% on average. And these were obtained based on our baseline survey data that we conducted in Nigeria and India. So just to emphasize. All right, great. Now to carry out the life cycle inventory analysis, we use both literature data and real life field data collected through the Cultivate app. The app gives us more of a granular input like temperature, energy, produce mass, and refrigerant type. And yeah, so this is good to emphasize. And then we also got data from EcoInvent database, the manufacturing website, and so on and so forth. Okay. And then we have a bit of the equation that we use to compute this electricity. I just wanted to emphasize this, right? So these are the core equations, and these equations allow us to then break down the electricity and material used in the cold room, whereby each step from the initial cooling to storage, maintenance, to battery charging, and even food loss is accounted for, while the outputs like refrigerant leakage and food waste are then used to calculate the emissions, right? Also know that the temperature in the equation is collected from the app. So not just temperature, even the mass, so which is the the volume of the produce stored in the cold room. So if you like to revisit the definitions of functional unit, input flow or output flow, and so on, you can find them in the FAQ under this video in the onboarding toolkit. Great. Then we go to the third step, which is the impact assessment. Um, we translate all the inventory flows into climate impact using the global warming potential, GWP, which is expressed in a kilogram of CO2 equivalent, right? So we use the environmental footprint 3.0 method from the European Commission's Joint Research Center with data and characterization factor drawn from EcoInvent 3.8 through CIMA Pro version 9.5. So these are basically some of the important steps that we took. So note that each input is then multiplied by its characterization factor. So for instance, the solar electricity, was 0.0757 kilogram of CO2 per kilowatt hour, right? And then we have the refrigerant as 15.124, and then we have the bio waste as 0.2127 kilogram CO2 per kilogram, right? So we then calculate the total emission for cold room storage using the equation shown on your screen, which is basically the summation of the product of the life cycle inventory data. So for instance, the input multiplied by the characterization factor, right? So this we did for cooling and then for without cooling. And then finally, the avoided emissions are then simply the difference between the emission without cooling and the emission with cooling, right? So this gives us a direct comparison between cooling and then no cooling scenarios. Great. And then the last step based on the four iterative steps or standardized steps of LCA is the interpretation. Here we would then interpret the result, and this of course depends on the use case, right? In our use case, what we wanted to show was the benefit of cooling. So the result was more of the CO2 saved or the CO2 avoided due to cooling, right? But anyways, when we put everything together, you get to see, we're able to see a very strong benefit. And then using a base case scenario for cold ops room in Ile-Ife, Nigeria, you could see already that cooling reduces emissions by about 61% compared to no cooling scenario, right? So this result shows that while cooling has an energy cost, the avoided emissions from reduced food loss outweigh those costs, especially when powered by solar. Okay, great. Um, Maybe we go to that, yeah, then we go to the next slide. Here you can see how we've embedded the CO2 estimation pipeline directly into the Cultivate platform, right? To generate real-time environmental insights. It's a bit technical, so I won't go into the technicality of this slide. But what I wanted to show is that it start usually with the power source. So we need to know the type of cold room that the fruits are being stored in. So is this solar, grid, battery, or hybrid systems? We supply the energy to the cold room. And then this cold room stores crates of fresh produce, and each crate is then digitally tracked through the Cultivate crate storage management system, right? And then from there, the data flows into the Cultivate database where we capture all the key contributors to the CO2 emissions. Now, with cooling, this includes electricity used for cooling fruits, charging batteries, producing ice for thermal storage, and then maintaining temperature, right? We also track the refrigerant leakage, food loss, and bio waste. So, for comparison's sake, we separately track emissions from food loss in scenarios without cooling, right? So, to process this information, we run a Python script daily, which then calculates the emissions and then store these results in the database. To maintain credibility and comparability, these calculations draw on standardized CO2 parameters from EcoInvent, is then adapted to specific context. So in this case, we adapted this calculation to India, Nigeria, the Philippines, and also a global average. Then finally, the processed data is made accessible through Cultivate Impact Dashboard, which is delivered via an API-based mobile interface. So this usually gives users and stakeholders real-time visibility into environmental footprint of their operations in order to allow them to monitor, manage, and ultimately reduce their emissions more effectively. Now, this slide shows you how the Cultivate app streamlines data collections for each code room setup, right? So users in this case can quickly enter all the key parameters needed for the lifecycle inventory. So for instance, the likes of the power source, whether it's solar, diesel, or grid, the storage volume, the installation details, even the refrigerant type and charge. These are information that we collect, from the user when setting up their code room, right? What is important is that anytime a user updates or modifies this input, the system automatically triggers a real-time recalculation. So this ensures that environmental impact assessment always reflects the most up-to-date conditions. This approach, in my view, makes this process more efficient and responsive, helping both the operators, the cooling service providers, and even the farmers and traders to see and then to track emissions accurately, and in order to optimize the performance of their usage. Now, in this slide, you can see how the Cultivate app goes beyond just data entry to providing real-time monitoring and actionable insights for each code room. On the far left, you could see an example of the temperature history. Well, not really far left, but on the left of your screen, You see the example of the temperature history, where user can track how the cold room conditions evolve over time alongside the current temperature reading. Now, why is this important for this presentation? This is because the electricity calculation also depends on this temperature reading in real time, right? So that's why it's important that the user or this yeah the users could see this temperature reading in case, for instance, there's an issue with the agrothermal sensor. Then this could also be corrected in order to make sure that the models are being fed with accurate temperature data. Now, on the right side, you see a sample of the app analytic view where users can then see instantly outcomes like the changes in the food laws, and also other comparison can be made, right? So, anyways, both visualization empowers the consumer, empowers the trader and the farmers, and also the cooling service providers with real-time information in order to make a better decision with regards to their environmental impact. And then in this slide, we show that the LCA results are presented also through the Cultivate Impact dashboard. So on the left of your screen, you can see an example where the user can track food loss evolution. As I said earlier, here the food loss has been reduced from 80% down to almost zero. Anyways, this is just an example of what it is, and not accurate data. The dashboard also shows the corresponding CO2 equivalent emission evolution. In this case, a reduction of over 545 kilogram of CO2 equivalent when comparing cooling versus no cooling, right? So this translates to emissions falling from around 46 kilogram per kilogram of produce without cooling to less than 1 kilogram with cooling. Great. Now, beyond emissions, this dashboard also summarizes crate management data. So, for instance, how many crates were check-in, check-out, and then detail crop distribution across different crops such as tomatoes, in this case, aubergines, bottle guides, strawberries, apples, and so on and so forth. Right? Detail about the crate management, has been explained in other videos. So please feel free to also refer to the onboarding kit for how this is being presented in the Cultivate app. Anyways, finally, the system then calculates the specific CO2 emissions by crop type, which provide users with granular insights into how each commodity contributes to overall footprint, right? So this is very, very unique because we can also see the contribution of each commodity being stored in the cold room. Now, by combining these views, which is food loss, emission, crop level, breakdown, storage activity, and so on and so forth, the Cultivate app empowers operators and decision makers to track their environmental impact in real time, identify opportunities to further cut emissions, improve efficiency and revenue, and then minimize waste across their operations, right? So in short, the dashboard makes the climate and economic benefits of cold storage visible, measurable, and then actionable. So this is very key for us to emphasize. Great. To wrap up, let's return back to the central question we began with. Is energy used for cooling justified by the environmental benefit of reducing food loss? Well, I would say it depends on the use case, but in our use case, the answer is yes, right? And we get to see that through the Cultivate app, we are now able to track the impact in real time because the system connects field data such as power use, temperature, food loss with robust life cycle assessment methods. So this basically provide farmers, operators, policymakers with insight they need to scale the cold storage operations responsibly. So for me, the takeaway is very clear. Could storage, can cold storage strengthen food security, improve farmer income, and contribute to climate solutions when deployed reasonably? The answer for me is yes, right? So This brings me to the end of my presentation. Thank you so much for your time, attention, and curiosity throughout this session. If you have any question, doubt, or if you're curious about anything, please feel free to reach out to us. And if you have more question about some of the terminologies used in this presentation, please, I refer you to the FAQ session just below this video. Thank you so much once again for listening.